Okay, we'll start. So, this is Gerald Jay Sussman, my mentor and good friend, who has probably taught at least a few of the people in here. He's one of Marvin Minsky's early students and has done a lot of interesting things in his life, and he's going to tell us about the latest stuff he's been thinking about. And that should be all we need to know.
Okay.
Jerry.
Well, you should hold on. I might not say anything you like. Anyway, one thing I'm going to start with is actually very old stuff. When I was an undergraduate, which was a long time ago, I suppose 64 to 68 at MIT, there was a fellow named Jerry Lettvin, who was a very interesting character, and I would go talk to him occasionally, and he had ideas about neurophysiology, which were mostly very good and sometimes wrong, but it didn't matter because his stories were so good it didn't matter whether they were right or wrong. In other words, they could be useful as ways of thinking for lots of things. And one of the things I learned from Mr. Lettvin was that that almost none of what we perceive is the stuff that's out there. That in fact we make up most of it. And in fact it's essential from his point of view, it was essential that we have to make up the content. And so I want to talk about filling in details, and basically that hallucinations are necessary in order to perceive. Okay, and then I want to show how that leads to invention of a kind of system for doing reasoning, which is not unusual, but which in fact mirrors that kind of way of working with the world. So, to get onto this, I see, good. Okay, let me see if is this thing actually winning? Hold on, what's going on with this little clicker? I may just have to do the standard thing. Okay, good. Let's start with, yes. Okay, first of all, so obviously clicker's battery needs replacement. The one thing is that the observation is that in order to actually to see things or to perceive things, you better fill in details. There are details that come from everywhere, that in fact it's essential to hallucinate the details if they're not there, and it happens very fast. Okay, so for example, if I, okay, I should have checked the battery. Look at this picture. Whoops.
There's a pause.
No. My computer is putting out on my screen. Oh, there it is. Boy, there's something weird here. Okay. Now, everybody see these two scenes? What is this? What's this? These are the same bit patterns, just flipped. Okay? You created the scene that wasn't there. Yes, these are the actual bits. See, here's the wheel that you see, etc. It's all there. Okay, it's the same bits. Okay? I got this mouth open, right? Okay. Here's another. Takes a while for this thing to respond. Okay. So here's another one. Do you see the triangle that isn't there? Yeah. Everybody sees it. Everybody knows it isn't there. However, you see it very well. Okay. Now this is obviously an important observation. And by the way, we know that bees do this also. They can see Kinesis triangle, but pigeons don't. So there's sort of a wiring thing. The way in which bees have been tested is you train a bunch of bees to go to a place where there's sugar water and one of these images, and not the case, just a triangle, and you move that around, and eventually you see that the bees will go to a Kinesis triangle. Okay, so that works. What are they? Well, there are clues here. There are local clues. There's this one which says, gee, there's some line that should be going, but it stops. Not only that, it's been intercepted by something. So this one over here. So maybe there's something occluding. This white object appears to be occluding this guy, and that continuation makes us feel that that's really right, and so on. So there really is something like that going on here. Okay. In fact, another thing, Dave Waltz, a great wizard of about when I was a graduate student, invented a mechanism of being able to label line drawings, so they could imagine there to be three-dimensional objects. Those of you, how many of you know about Waltz labeling? Good. Okay. What's happening here, if you look at this is saying that this is a line that's sticking out at you. Okay, that's sort of a fold like this, and this one -1 is inside. So this is some sort of little depression in the surface. Okay, this one on the other hand, this means it's an open area that behind here is nothing. So this is a hole that goes all the way through. Okay. And whereas this one over here we're looking at something in space, floating in space, which is coming up and is like a truncated pyramid. Okay? And this one is on the table, but it's a truncated pyramid. Okay? So that's examples. And there are certain, these are little programs that he wrote, which were beautiful, which could take a bunch of lines and produce these labelings. The way they did it is quite clear. In this case, it was, well, all possible labelings of that corner are known. There is some sort of catalog of them. All possible labelings of any corner are known, but there has to be arc consistency when the lines come together. They have to be the same label. Okay, and that's all. That's the whole thing. It's very much similar to what I showed you before with the kinesis triangle, that local evidence is being put together to make a global interpretation. Okay? And of course, here's one that I got involved in 1975 with my friend Richard Stallman, who, by the way, also is the reason why you have free software. And in fact, your company is probably dependent upon him. But in any case, Richard, when I was beginning as an assistant professor at MIT, around 1973 to sometime later there, I was teaching the introductory electrical circuits class some of the times. Okay? And I observed that the teachers didn't teach the students what they did. What the teachers taught the students is lots of little equations, when then you have to make up equations for each of the parts, make equations for the ways they hook together, and then you solve the equations. But unfortunately, that's not what a real electrical wizard does. Okay? And so I decided it was important to try to figure this out and then write a program to do it. And part of my intention was to take the programs, write them so clearly that I could give them to students could read them, and then they understand how to do it. Okay? Let me show you what I do when I see a circuit like this. You're about to see a shtick. Okay? I do this all the time, but it doesn't depend upon the circuit. I can pick up lots of circuits like this. This is a 4-transistor, not very good quality amplifier, audio amplifier, and I'm going to assume that all the transistors are in the active linear region, which means that the base emitter junction is going to be 0.6 volts approximately, okay, and that there's no current going into the base of any transistors. These are approximations which may be false, but I may have to verify that later. So, knowing that, I'm going to say, gee, I know the voltage over here and I know the voltage here, and this must be a voltage divider because no current in the bias approximation I'm about to make goes through the capacitor, and no current goes into the base. Therefore, I know the voltage here, which is the voltage division ratio for these two resistors. Since I know the voltage here, I know the voltage here is 0.6 volts below it, which means I know the voltage here is 0.6 volts below that. So I know the voltage here. Given that I know the voltage here, I know the voltage across this resistor, so I know the current through it. That current must be coming, well, it can't be going into a base, so it must be coming, well, it can't be coming into this base, so it must be coming through here. Okay, because of the conservation of current. And that means I know the current through here, but I know the voltage here, therefore I know the voltage here. This voltage is 0.6 volts below that. These are two resistors in series because this is open circuit in the bias model. And so therefore I know the current through here, therefore I know the current through here, therefore I know the voltage here because it's 0.6 volts down, and therefore I know the current through here, so I know all the bias conditions within a few percent. I'd have to verify that this was true. The way I'd verify this is true is I've computed a current through the emitter junction here. I know that there's a transistor's beta is about 100, so this has to be 100th of that current, which means that there's 10,000th of that current over there, which means that is that 10,000th of whatever current I computed here, a significant amount of the voltage there, it's going to make a difference. The answer is no. Okay, and that's the most important check. Okay, so what you've just now I could also do the incremental. I could get you the frequency response, all sorts of things like that based on what I just showed you. I'm not going to go through teaching you electrical engineering. I want to show you a method by which I'm reasoning, which is I'm using local information and propagating it around as far as I can. Okay? And that I'm using the diagram as my memory. That is, the diagram has a finite number of places on it to write things. And if I were actually doing this job, I'd be writing down the answers at each place that I computed so that that would be the thing I remember, and I could trigger off the stuff that I'm seeing nearby. Okay, so there's a local analysis there. If this was more complicated, there might be one simultaneous equation, like if there's feedback, okay, for a feedback amplifier, or one equation and one unknown. If it might be two equations, two unknowns, the most horrible situation I can imagine. Okay, that's what real engineers do. Okay, so that's one thing you're seeing. Here's another. Here's something. The idea of, look, you are at home in your bedroom. An elephant appears just outside the bedroom door. Can the elephant come into the bedroom with you? Anybody know? Why not? The reason is the elephant's too big to get through the door. Right? That's the think of it that way. You look at the thing and say, my gosh, I know what an elephant looks like. It ain't big. My door isn't big enough to do that. Okay? That's you're constructing a visual image, okay, which is then being run by your visual system and then being analyzed in such a way as to produce the answer to this question. Okay? And that's another example of such a thing. Okay? And look, here's a really interesting thing. What's your name? Okay, that was 500 milliseconds at most between when I finished the question he answered. Okay, half a second. Well, a neuron time is about 5 to 10 milliseconds, the fastest a neuron can do. Therefore, it's a few tens of steps. Okay, I don't know how to make a computer. I don't care about how parallel it is. That's a completely different question. How do I solve the problem of doing phonology, the morphology of the words, the syntax, the semantics, and the problem solving, back to the syntax, back to the morphology of words, then the phonology, okay, and then produce the muscle movements to just answer the question in 500 milliseconds. There's not enough time. It means we don't know how to compute. Okay, so that's one of the things that's bothering me for a while. I mean, now, yes, our computers are a billion times faster than that, step by step, but that doesn't help when you look at a problem like this. Okay, we really don't understand what we're doing, which I think is very important. Okay, so I'm going to tell you about a particular model of computation, which is modeling what I'm talking about. Okay, I'm imagining a mechanism made out of lots of little autonomous machines. Okay? Each machine is basically looking at neighbors, at those little cells that it connects to. These have nothing to do with biological cells. Okay? They're little cells, and the cells contain information. And when information appears in some of the cells, a propagator might say, oh, that's enough information for me to change something else. Right? That's all. Okay? So this is a nice little model. It certainly has the nice properties that is certainly scalable. It's got nice, in fact, because everything is nice and local like this, it also turns out that it can avoid lots of the problems of parallelism when you're trying to simulate serial things with parallel. Okay? The hard thing is not making parallel machines. The hard thing is simulating a serial process on a parallel machine. Right? If we start realizing that what we really want to do is write parallel processes in general, then this problem mostly goes away. But there's a breakthrough that makes this even more possible. And that was by my graduate student, Alexei Radul, who finished in 2009, I suppose, with a doctor's thesis. In fact, his breakthrough is that the values that are in the cells are not the values like 32. They could be, but they might be something like information, like that value is greater than 5. And it's less than 100, okay? Partial information, okay? And that only thing a propagator could do is increase the content of information in a cell by restricting the possible values that could be there. Okay? This has a super wonderful property from a parallel processing point of view that, in fact, things eventually converge. It's an eventual consistency feature. So that's this information cells monotonically information, and you can imagine things like I gave an example of numerical intervals, but unification patterns that people use in things like logic are perfectly plausible such things as well. Okay? Also, algebraic expressions merged by equation solving. I don't know what to do about probability distributions. I don't understand probability. I can assure you that. There has been, of course, this wonderful pile of work by all the wonderful Bayesians, which have taken over the world for good reason. That's E.T. Jaynes basically is the founder of that stuff, and the other end of it is the people who were opposed to him was I suppose Mr. Fisher of Fisher Information, and they were fighting for years before we got involved with computers, but the remarkable thing is that they're both right, so we have to be careful. Frequentists and Bayesians are right, and they argue all they want, but they're asking different questions. But that's a whole different story. I'm not going to get into that today. But the answer is, probability is pretty bad for a reason. Okay, I've got to be careful about it. Mr. Jaynes, in his second chapter of his book, explains that logic is a is actually a sub-theory of probability. It's a specialization. Now we know that logic is at least exponential in solving problems, SAT problems, for example. Okay, so that's awful. Okay, probability must be worse if we actually want to compute the distributions. Okay, because if we can compute the probability distributions, we get the answers for the logic. So I can't believe that that's an effective mechanism. On the other hand, there are some very smart people, one of whom you may have heard of, Vikash Mansinka. Anybody know who he is? Yeah, that's somebody who knows. Okay, he's just recently got a doctor's thesis for working for, I just lost his name, Josh Tenenbaum. Okay, where he approximates probability distributions by sampling. Right? A very elegant piece of work, and I highly recommend reading about it. Okay, so, but I really don't understand probability. Okay, I'm going to give you an example. I'm going to give you first an example which is purely about how to use propagators to, I'm not going to tell you how they work inside because it's easy. And I highly recommend reading a paper by Alexei and me called The Art of the Propagator, which explains basically how to write the programs. Okay? In fact, it turns out that the paper is also executable, as, by the way, is his PhD thesis. It's written in a form that it can be loaded in an appropriate way into an MIT scheme system, and it will just run. Okay? It's sort of a literate programming style hack. But in any case, I'm going to tell you something I know a lot about, which is astrophysics a bit. How do you estimate the distance to a galaxy? This is a giant galaxy in the Virgo cluster, M87, one of the largest galaxies we know of. It's giant elliptical. It also has some horrible jet coming out of it, which I can't see here because it's deep inside, which is coming from a central black hole. Now, I'm going to make up some propagator cells. Specifically, I'm going to make up a cell for something called the distance modulus. And you don't have to know anything about what these things mean because it's not relevant what they mean. Okay? I want you to see how things hook together. Okay? So I have a distance modulus and a distance cell. Right? This is the first step. Distance modulus is something you measure by looking at the intensity of the light coming from this object, what out there, and having an estimate of the actual absolute luminosity. And since the light goes down as an inverse, you get the inverse square law from something at a great distance. If it's approximately a point source, which everything out there is, then what you end up seeing is an estimate of the distance. It's an easy computation to make. Okay, and if you want to see the insides of the propagator, I'll show it to you later. I have it on some very late slide for answering questions. So here's a propagator called a constraint propagator, which connects those two. A distance modulus to a distance, okay? And I'm going to pass in those two. So I'm wiring it together. That's a wiring. Right? So imagine these little machines being made. Now this little calculator, propagator is sitting there looking at these cells and saying, is there anything I can see happening in them? Well, they currently have nothing in them, so nothing interesting happens. I'm going to tell the MA distance modulus that the value is 31.43 plus minus 0.3 in some units. Okay? I can tell you what those are. It doesn't matter. And it was told to us by Vandenberg in 1985 when he took some images. So he produced a big table of things that you find in the literature, of the astronomical literature. I think that was an APJ actually, where he has a table of lots of galaxies he figured out distance moduli for, and they were pretty good estimates. So I can now ask what is the distance M87 in megaparsecs, and I get, well, it's 1945 plus minus 2.678. Of course, this is nonsense. In astrophysics at that time, we'd be lucky if we got the sign of the logarithm, but indeed this is what you get from at least his estimate. Okay. Now, so this is what you're seeing immediately from here is that I now know that I got this information by propagation from there. Okay. That's provenance is being carried. I can ask various explanations, like, gee, how do you know this? give me a level 2 explanation. This is a very simple explanation. That's what that little 2 is up there. And it says the stupid thing. It says how I got it. Okay? What happens is that the user, that was me, typed in this information. This is actually an interval. Okay? And Vandenberg 1985 was the premise that I specified. Okay? So there's a premise that's modulatable, actually. It could be either true or false. Vandenberg might have been wrong, okay, and probably was. In which case, however, that was propagated through the muted D, P rather than C. C was the constraint that goes both ways. It's made out of 2 constraints, one which goes from distance modulus to distance, and one goes from distance to distance modulus. So inside, there's a combination of 2 little formulas. Okay, so that's what that's saying. Okay, and it computed on those and got this value, which is again an interval. Okay, I could ask for a more detailed explanation. I'm not going to go through a detailed explanation, just to give you the idea. Well, you see, I'm now opening up these propagators. Okay? And one of the most wonderful things about this kind of system, which we discovered, Stallman and I, way back in 1975, was that one of the best ways to use a program that helped you build electrical circuits or gave you a sort of partial analysis of an electrical circuit was you could ask it, how do you know that? Right? For example, it's possible that if I'm designing one and I specify a particular resistor and supposing I'm making an amplifier and I want a certain amount of output swing, I've got a voltage maximum, I'm going to specify a current through the output transistor, and I also put a resistance for the output resistor there. And if it turns out to be inconsistent with the output swing I'm going to get, perhaps, because I would cause the thing to go above or below the maximum voltage. Okay. Well, I would get an argument from the computer. Say contradiction. The following constraints are in contradiction. Okay. You put in this much, this, and that. Those. Here's the reason why that can't work. So that's very. We've actually used that for teaching to some extent in some of our electrical circuits classes. So you're getting an argument is a good thing, okay? But you see, I'm going to tell you more about this. So I suppose. Okay, good. That was the right thing. Okay, so yes, I'm always freaked out by the fact that it takes a second and a half or something for the projector to figure out what's on the screen. I wonder why. What's it doing? Huh? Okay. Okay. Well, anyway, what we're seeing here is that John Tonry, who's a professor at University of Hawaii right now, he was at MIT once, had an estimate of the distance to M87 by something called the Surface Brightness Fluctuation Survey. Again, you don't really want to know, except that the galaxies are sort of granular because they're full of stars. And you see the granularity. You say that if it's very far away, it's very good. It's going to be very hard to see the granularity. If it's very close, the granularity is clear, and you estimate the distance by that. Yes? So that's the kind of thing. And he got an answer, which was the distance was 17 megaparsecs plus minus 0.31. Now, if I ask what the distance is now, it actually contains 2 pieces of information. Because the interval produced by Vandenberg overlapped the interval produced by Tonry. Okay? And that overlap meant that there was a better estimate, which is from there to there. Okay? So that was computed, and there it is, 17.07 plus minus 0.24, whatever. Okay? But better, if I go back and look at the distance modulus, it's been improved also. Because the information that was increased in one of those cells simulated the back propagation of information to the other, which said, oh yes, that's a good thing. Okay? And collected it because it was an improvement. Okay? It was more information. Okay? Now, we can talk about things like redshifts. You probably all know about Hubble's law, which says the further away something is, the faster it's going from us, because the universe is expanding in some funny way that can be explained a little bit with Newtonian mechanics, but a lot better with general relativity. I'm not going to get into that. I apologize. General relativity is another couple of hours of talk. But in any case, the redshift, which is a measure of the wavelengths of light coming from this object, there are discrete wavelengths coming from spectral lines, and they're shifted to the red because of Doppler shift. Things moving away from us, it's red. If we're moving toward us, it would be blue. Okay, so we have a red shift. We connect it to a radial velocity by some nice formula which connects them, and I'm not going to put it up for you. That one's actually complicated because it does depend upon special relativity at least. But there is such a formula, and it's actually two, one in each direction. And if I say that the redshift of M87 is that, measured by Mr. Smith, then the radial velocity for M87 is that. Okay, just computed the standard way. But now I can hook it together with Hubble's law. Okay, I can say that, well, a redshift and the radial velocity are connected. I'm sorry, here it is. Here it is. I can make a Hubble constant, which is the rate of that's the Hubble constant. It's the amount of velocity you get per going for a particular distance. It's kilometers per second per megaparsec. Okay, actually, is the units we use. Yes, it's a very unusual unit. So we're going to have that, and we're going to connect up this is the radial velocity with Hubble's law, and this gives us an estimate of the Hubble constant, which we got from Tonry, Vandenberg, and Smith. Okay, but actually there has recently been satellites like the Wilkinson anisotropy probe, which gave us better information about the Hubble constant. Okay, I'm not going to explain how it does it, but by certain things we measure from these satellites, we can look at. What we're looking at is the cosmic background radiation and the statistics of that. And from that we get a pretty good estimate of the Hubble constant. It's 73.5 kilometers per second per megaparsec of at plus minus 3.2 from the Wilkinson anisotropy probe, and that gives us a distance which is very good. Depends upon all of these. Okay, but guess what? There's even one more thing I'm going to add. There's a theoretical point called lambda cold dark matter. There's the universe is full of stuff we don't know what it is, called dark matter. And there's a particular model for it called the lambda cold dark matter model, which is currently agreed upon by lots of people. Okay, and you can argue about that if you like. And if I tell it an estimate that I got from that, it says, oops, there's a contradiction between two of these measurements. Mr. Tonry's measurement is incompatible with this assumption. Okay? Now, that's very important because, first of all, at least one of these is wrong. Probably both. Okay? But the really important thing is that what's the truth if I believe one or the other? I should be able to modulate my understanding. Okay? I should be able to say, if I believe a certain set of assumptions, what's true? If I believe another set of assumptions, what would be the consequence? Okay? And in fact, there could be programs that might have to try to resolve this by saying, what are the actual details of how these interact? Is there somebody else who can give me information that will clarify this matter? So you could have a program or a person whose job it is to look at both points of view, to examine them and see how they fit. Yes, sir?
If there's a cycle in this lattice of nodes,
lots of them.
how do you decide when to stop propagating information?
Because the information is monotonically increasing in a cell.
So you reach a fixed point.
Where you fix a fixed point, right? Okay. If the cycle were something like the convergence of square root, it would take a lot of work. Okay, but for things that I'm showing you here, there are one or two steps. Okay. So if I retract Tonry as being the source of the information, say maybe he was wrong, well then my estimate for the Hubble constant is this, and it only depends upon those two. Whereas if I retract WMAP, lambda cold dark matter, and assert Tonry, then I get the Hubble constant being dependent upon these and W map 3, but not without that lambda cold dark matter assumption. Okay? So what you're looking at is, first of all, what the nice things you could do with these propagators. I can imagine a very important consequence, independent of anything else. And that, almost all, as you probably know or have read, I suppose Ioannidis wrote a paper explaining why almost all medical papers are wrong. Has everybody read that paper? Worthwhile. Ioannidis. What he was, a very quick and dirty summary of it is that since papers written in medical journals require a confidence of 95%, which is, right, 1 in 20 experiments are wrong, okay? And since everybody does hundreds of experiments and only publishes the ones that pass these confidence measures, then almost everything in the journals is wrong, okay? It's very sad. Cake is he's probably right. Now, of course, I've also seen, having been on the scientific advisory board of an organization that deals with multiple sclerosis, because I had a student in my class who got it and asked me to be on this scientific advisory board. I've heard also horror stories about medical data being completely wrong for other reasons. Here's a beaut. Most medical data is collected in Excel spreadsheets. Now, most medical doctors who collect this data don't have the foggiest idea what an Excel spreadsheet actually does. Turns out there's an option whereby you can sort a column without keeping the rows sorted. Much of the data examined by my friends in this multiple sclerosis foundation much of the data has been mangled in such a way that it can only be explained by this. Okay. Okay. So there's a lot of very bad stuff out there. Okay. I believe we should have shot the guy who wrote Excel, but that's no longer available as a problem to be solved. Okay, so you could imagine that one of the things we could do to improve the world is collect a lot of the medical papers and journals and biological ones, all the ones that have these flaky low confidence. When you look for the in the physics world. Recently, we found the Higgs, right? You had to have at least 5 standard deviations before anybody even began to believe it. Okay, and they won't be happy till it's at least 7. Okay, this is nothing like the kind of stuff going on in these other places. But of course, the reason is it's too expensive to experiment on people. It's very inexpensive to experiment on very large numbers of particles. It only takes billions of dollars. So yes, sir.
So I just have one question about this
Yes.
slide here. So presumably you have these different measurements and they're linked behind the scenes by various formulas and whatnot.
That's right. Like imagine a spreadsheet, but imagine one that's got all different directions. Right. Now I can show you the details of how that works.
So I mean, it seems like it might be that supposing you use this as information, it says there's a contradiction because the ranges don't overlap. But supposing like one of the formulas inside, if you tweak the coefficients just a little bit, it would suddenly all become.
What you're saying is maybe the formulas are wrong.
Yeah.
Well, of course. Well, to be perfectly honest, if we were doing this seriously, the formulas are premises, just like the measurement Vandenberg or whatever, and they would just be too long to put on the slide. In fact, I do it that way. I can attach those as well. Okay.
I mean, you wind up with a sort of exhaustive sort of set of like a lot of different dimensions.
Well, some of the things you want to be careful about, like, do you really, for ordinary physics, do you really care very much about F equal ma being tentative? I would hope not. Okay, so you see the thing is, there's what you want to see. Now it's a question of presentation. What do you think are the delicate things that are the current data that you're investigating, and what are the things you want to say, I will assume for the sake of argument, are correct now? Okay, and of course that has to do with presentation. That's nothing to do. Look, I'm giving you lots of parentheses. Come on now. I mean, I'm a Lisp guy. Okay, I'm not talking about presentation here. Okay, you're talking about machinery. Okay, let me talk a little bit about something else now. I want to pop into talking about how you do more general problem solving. Okay, because what I've shown you now is calculations, plumbing, infrastructure. Okay? The type of things I've talked to you about is the mechanisms for shifting data around in a way that you could imagine being scaling at all levels. You could have individual chips, or even tens of thousands of little propagators on a chip, and then you could imagine them as network wide as well. Because all they are little independent machines that are sitting around talking to their neighbors and asking, have you changed? Do you have some information for me? Can I change that one? Okay? That's all that's happening. So it has nothing to do with computer language either at this level. This kind of thing can be done in any computer language, and languages could interact, because all that really matters is that there be a set of an API where these propagators could talk to each other and maintain contents of cells. And the merge procedures would have to be universal. But now what I want to talk about is a little bit of the important thing you saw there was the dependencies. The dependencies are the information that the reason why you believe something or not. And it turns out there is a kind of logic that was it's popularized. There's a book called Introduction to Logic by Patrick Supes from Stanford, I suppose. Written maybe in the 50s, I'm not sure. It's one of my favorite books. And where he actually shows how you write rules of inference in a way that allow you to follow out the arguments and keep the dependencies. So for example, here's his modus ponens. Okay? Modus ponens is, if A implies B and A, then you believe B. Okay? But here's the story. A implies B has a name. It's statement number n, or statement named n. It doesn't matter. Not that they're numbered is irrelevant. It's identifier of that proposition. And M is A, okay, and O happens to be the conclusion, the name of the conclusion. Okay? This is the reason. This is the argument reason why I believe some of these. So I left it out because I don't really care. If I don't know why I might believe N or M, but I believe them for some reason. Like I conclude B, it's because I used the modus ponens rules on N and M. Okay? But there's an extra column which is very important. That's the set of premises on which this depends. Okay? So that the premises, that's the thing like Vandenberg 19 whatever. Okay? So this is the premises of N are D1, the premises of M are D2, and the union of those is the premises that O depends upon. They don't always union. You want to be careful about that. So for example, there's the deduction theorem, also known as conditional proof, which has the following rule of inference. It says, if I believe a premise called A, that was something that was introduced as a premise, hypothetical. Okay? It might not be true. It's just something I introduced. And if by some reason I conclude B, I also get B, okay? Then I can conclude A implies B by the conditional proof rule, where the dependencies, the premises of D minus N are the reasons I believe it. Okay? Now that may not be obvious to you. You have to think about it hard, but it's true. Okay? This is a different kind of rule. Okay? And it just shows that the premises don't add up necessarily. Okay? That premise that I introduced over here, which is just the set of N, is the premise it depends. The set of premises it depends on. It depends only on itself. It's a thing that was introduced. Okay? And I can sort of subtract that out as from that set. So one thing this shows you is that once you have these propositions and they have names, you got a little more power. But I'm going to tell you more. The power will improve. Okay? So these handles. So supposing we are in a situation, and we're not really talking anymore about logic, useful rules, rule-based systems. And I have A owes B an amount of money U. And the reasons we believe that may be D1, okay? And B owes C an amount V, and U is greater than or equal to V. Then it's one way to solve this problem is get A to pay C by the amount V, and A to pay B by the amount U minus V, by the split rule, okay? with these guys. Okay? Now, unfortunately, this may not be a useful rule in every situation. What if they're 1,000 miles apart? Okay? However, if they happen to be at the same restaurant, okay, they're in the restaurant, then this rule is suddenly useful. And furthermore, the reasons for believing this is the correct result do not depend upon the fact that you're in the restaurant. The argument might depend upon it. That is what you would tell people why it happened. Okay? But the ultimate premises do not contain the restaurant part of the information. It shouldn't. It doesn't matter whether or not you're in the restaurant. This is still the right answer. Okay? Now, why is this important? This is important because much of the reasoning we do has to be specialized. It's very expensive to use modus ponens. It applies to anything. It's easy to make infinitely long deduction chains. But in very particular circumstances, it is appropriate to use it. When, for example, I need the value, if I have a proposition that might be very complicated, but I need that answer for some purpose, then it's appropriate to, and I also happen to have an implication that gets that in the right-hand side, then it's probably worthwhile to investigate whether or not I can get the antecedent of that implication. Okay? I don't want to in general investigate, I want it for that particular case. Okay? Similarly, so backwards chaining is helpful in a sense, as a request grant protocol or something. I'm not going to do any work unless you need to solve a problem unless you need the answer to the problem. But the other way around is true too. I'm not going to do any work trying to figure out what's needed, unless I've got enough evidence that it's worthwhile to do some of that. That I have some basis to start with. Because backwards chaining can get you into horrible trouble producing a very large number of sub-goals, none of which are real. Okay? None of which could ever be satisfied because they might be even wrong. Okay? On the other hand, forward chaining can produce a number of conclusions, none of which are irrelevant to your problem. Okay? It's easy to generate those cases, okay? Even with little genealogies. So here's an idea. I'm going to start talking about, first of all, that propositions have more than just true or false. Okay? This is not, by the way, a multi-valued logic. That's not the goal. That's easy to simulate in ordinary logic. But what this is about having more power to write rules that depend upon our states of knowledge. So, for example, let's assume I'm not going to use words true and false because I don't know what that means. That's relative to a problem and a situation and all sorts of things like that. Okay? But it may be that from the point of view of some worldview, some set of presumptions, some assumptions, some premises, okay, a proposition may be accepted. That's the equivalent of true if I believe everything else that's relevant. Okay? Or it may be rejected. Okay? I know it's false. Okay? It could be known if either it's accepted or rejected, or unknown if it's neither. Okay? And it could be a contradiction if it's both. That is, my head's wrong. Something's wrong in there if I believe both something and its negation. Okay? So those are states of mind of a reasoner about a particular proposition. Now those could be represented as cells in a propagator system, and then there are connections among them. Like, for example, simple things like this: the or of the accepted and rejected is the known. Okay? Where the not of the known is the unknown, and the and of the accepted and rejected is the contradictory, and they can be connected together around. Okay? And rules can start using these kinds of information. Now, what do I get out of this? I can write rules like this. A much more powerful version of that. Well, here's the one simple one. This is actually, I'm not even going to, I'll show you two of them. This is the game of the restaurant thing. If the proposition, this is just a saying, the proposition represented by the Lisp S expression, quoted mumble here, that proposition, if that is an accepted thing, if the acceptance of it is named M, That is, the cell that contains the belief of is it accepted or not. Okay? And N is the O's, A O is B, U. And O is B, O, C, V. And if the amount of remember, again, this is not written to make it easy for people to deal with. Okay, this is my machinery. Okay, this is, I'm sure we could write nice things that present this beautifully and this with syntax and all that. This is Lisp. Okay, this is what I like to write, having had many years' experience with it. But now the expression propagator P is equal to the Boolean value, which is if this is the pattern value of U and the pattern V in these two expressions are if that is numerically larger or equal to. Okay? So I've got that. Then it's worthwhile accepting this. That you have to do this work. This is just saying the argument, and this is saying what it depends upon. Okay? And notice that the restaurant does not appear in what it depends upon, just the argument. So this is building structure that way. So that's easy. I'm going to do something a little better. Okay? Here's a big one. If I have handles, if I have the name, if I have some way of grabbing a proposition, and I have dependencies that say what that proposition depends upon, what are the premises that it depends upon, not the argument, the premises. Okay? Then I get control out of the situation. And imagine how this works. Okay? Here I have, these are a proposition. Please show B. Somebody wants the answer B. It was asserted. It's a piece of information. This rule, when this rule fires, G is bound to the acceptedness of that proposition. That is, that whoever is doing this deduction believes that. Okay? It will only fire if that acceptedness turns out to be true. Okay? In the context of that rule, other rules are created. Okay? This rule is created. This rule says, and this rule depends upon the previous information. So this rule which says if I know that A implies B and I call that I, okay, this rule will only get created with very specialized B if I want to show that B, because these share the same name. Okay, so this is a standard sort of thing you do in logic. Okay. However, this rule is specialized for the particular B that was B I'm looking for. If that implication appears, then there are two new rules that are relevant here. Okay? One of them is if it turns out that that I happen to know A, okay? Well, then I can assert B for the reason that I know these two. I don't care that I was looking for it. Okay? So logically, it only depends upon two of those antecedents. It doesn't depend upon all three. The fact that I know that B is true from me does not depend upon the fact that I was curious about B. Right? But even better, okay, it's only worthwhile chasing down A if it's unknown. Why do any work if A is known already? So if A is unknown, okay, then it's worthwhile producing a please show assertion for A. Okay? And indeed, this one depends upon the goal up there, the fact that I have an implication, and the fact that I don't know P. So if P ever becomes known, that rule that's this assertion, the please show A, goes away. Okay, and therefore will no longer stimulate any work to be done. Right? So that in fact I'm controlling the deductions that are being made by by, in fact, depending upon what things I already know and what things I need, and that they could be interwoven in some nice way. Yes, sir. Where were you? You had a question.
Is this the same system as your earlier astronomical example?
The astronomical example it showed you the propagator system. This is showing you a problem solver built in the using the propagator system as the infrastructure. It's the infrastructure. It's in the propagator. The propagator system is being used to represent these cells, which are being manipulated to carry the dependencies.
It seems like in your initial example, if there was more to something than just the states known and unknown, because those ranges.
Yes, of course. That's true for that. That could be true too. Okay, I'm showing you an application. Okay.
So in that situation, known and unknown are sort of not used.
In that one, I did not. That one, I didn't tell you anything about known or unknown. That one, that was where it's purely numerical intervals as being the partial information structure.
I'm confused how known and unknown, if their infrastructure, are being used in that computation.
No,
They're not.
They're not.
Okay.
This is about propositions.
Okay.
Okay. And there's a rule system with the infrastructure, in some sense, the underlying library being a propagator system, allowing the manipulation of unknowns and knowns and all that to buzz along under the table.
So
Okay?
it's kind of, you've given me two examples, and this is the machinery for the second example. Is that right?
I'm not showing you. I'm showing you an example in this right now. I'm not showing you the machinery for it because that's itself very complicated. I've shown you none of the machinery.
Okay, so this is not part of the machinery.
No.
Okay.
This is a rule written for a rule-based system that is built on top of the propagator system. Got it? Okay. Okay, so that's what I was showing though, is the rule expresses the ability to control forward chaining by needed results and control the backward chaining by available facts. Okay?
It's analogous to Prolog in some way, in the sense that you're trying to make sure your system converges faster. Without this, it would still converge, but it might take an exponential.
No, it might not, because it might go forever. In fact, Prolog often does, right? And the reason is because if you do Prolog is doing pure backward chaining with chronological backtracking, right? By the way, this is doing smart backtracking, dependency-directed backtracking, which is the same thing as in the SAT solver world, you would call that causal learning, okay? But that's a separate issue, that's under the table. It's all running under the table, okay? The crucial thing going on here is that this is doing actually mostly forward reasoning, mostly antecedent reasoning, and the reason why it's doing that is because the statement that I want to show something is a statement that's something I might or might not know, or I might not care about, but it's there. There's such a statement. Let's create it, and it sits in some database and gets examined by appropriate rules. Okay. Okay, I'm almost done actually. So what? I'm very good at talking for exactly the right amount of time, I think. This is the idea, what I've shown you, that the plumbing, that's all it is plumbing. Okay? The nice thing about the plumbing is it doesn't, unlike something like, what's a good one here? Logic. Okay? It's got ontological assumptions. Logic it makes you worry about everything. Writing programs in Prolog is hell, to be perfectly honest. Okay, to understand what they're doing is hell. There are other ones, good rule-based systems in general, or whatever. You make things that are object-oriented. Okay. Now, when you have your object-oriented program, it's pretty hard to write something functionally. If you're writing a functional program, it's hard to write an object-oriented. There's all these built-in barriers for thinking. You're stuck in one kind of thinking or another. And my image of the way to do things is I'm what's the right word? A libertarian programmer. Okay, and maybe a liberal politically, but I'm a libertarian programmer. That nobody's going to tell me how to program. If one of these propagators has to be written in assembly language, it'll have to be. If another one happens to be written in Haskell, well, I'll put up with the syntax. Okay, but the fact of the matter is, it doesn't matter. Okay, the propagator idea is independent of language. Okay, so the other thing is that once you've understood that model, it's basically parallel, and it's a nice way to build and use constraint systems. It allows you to escape from the expression-oriented mindset. That doesn't mean you can't compile a expression-oriented language into it. Alexei did for most of Scheme. Chris and I are now trying to do a different way of doing that. That's what we've been hanging out for. It's been very hard, but we've only been at it for a week. Okay, to make a different way of compiling it into propagators. But the other thing is that there's a natural way to track provenance, because what you're seeing is the appropriate tubing and generic operations that are happening there carry the provenance around as an example of metadata. There's many kinds of metadata, of which provenance is one. Okay. The nice thing I like is a way to work with locally consistent but globally inconsistent data, and there's under the table a SAT solver, which is, I mean, it's distributed. It's not a little program called the SAT solver. It's a distributed thing which knows about contradictions and how to resolve them by getting rid of some of the some hypotheses. And basically there are hypotheses that are labeled as hypothetical, and therefore ones that can be modulated in their truth. And that's the end of that. Now I will answer questions, but I also have a lot more to show you if you want. I can talk for many, many hours. Okay? Yes, sir.
So, if you went back to the previous slide, you say we have a way of managing locally consistent, globally inconsistent data.
Oops.
From what I saw in your examples, it was mostly you had the infrastructure to be able to claim and retract assertions, right?
Among other things,
and,
yes.
And you can juggle which ones you want to believe and see, tell me what happens if this set is true, or if I believe this set. Have you also built out the way to say, show me the conclusions down both inconsistent paths and see how they...
Yes and no. I'll be careful about that. I know how to do that, but the particular system we have doesn't.
Okay.
The reason why the system we have doesn't is because there's a single worldview in it at any moment. It's
Right.
time modulating it. But in the but there's the truth maintenance systems of there's a whole book about them by my former students, I suppose Ken Forbes and Johan de Cleer, which is called what's it called? Building Problem Solvers. It's Building Problem Solvers, where he describes how to make truth maintenance systems in general, of which one of the kind will allow you to look at all of the consequences at once, all the alternatives.
And then a related question I had on this was, you can say, okay, well, either this is true or that's true, and maybe some of the assumptions and rules, like F equals MA, I'm more confident in than others. Have you incorporated confidence
No.
metrics into this?
I have done none of that. Okay?
It seemed to me like that dovetailed into the fact that you said you didn't trust probability, you don't know how to combine probabilities. Is that the same issue?
Yes and no. Actually, the answer about the probabilities is that I'm afraid that once you have probabilities, you will have computations that never converge. Okay? If they're done, if the job is combining probability distributions, densities, the functions. If your job is estimating by sampling, which is what Vikash does, then you'll get some answer like you get with Monte Carlo methods, but it won't be. But you can't guarantee it. Okay? Yes, sir.
This is somewhat related, but is there a way to weight the provenance that you compute so you can say how much relies on this fact or that fact, or what makes it?
Well, you're asking like what things would you tend to retract if you found a contradiction? That's essentially the same thing. Well, you would put an ordering on what premises you would mark as hypothetical. That mark would say could be sorted. You could sort on that mark, and therefore decide what order you would want to retract hypotheticals. Yeah. Yes, sir.
I think it's still on a different tack. Some premises might just, if you remove them, might destroy like all of the other things that you had built, and others might destroy. Oh, well, this last step was wrong, but everything else stays fine. If
Yes.
you take that one out.
That's right. That's why F equals MA is pretty valuable. Okay. Yes. That's right. And so you're asking whether you can estimate ahead of time?
Yeah. Or,
I don't know. Okay. I haven't done any investigation into estimating the damage done by retracting hypothesis. Yes.
I would assume that when you're working with a system like this, that the provenance is also of tremendous value for debugging.
Oh, yes.
So with debugging, there's this, if we divide bugs crudely into these two categories, the computer did something that I didn't expect. Why did it do it? And the computer didn't do something that I expected it to do. Why didn't it do it? Provenance is great for the first, but the second one, I mean, if you expected it to produce an answer and it didn't produce it, or it produced an answer and you expected X to be a contributor to the answer, and you take a look at the provenance and you see that X is not in the
Absolutely.
contributions, how does this provenance system help you figure out why?
Well, remember, there's two parts to it. There's the part which is the dependencies, which are the lists of premises that something depends upon. And there's also the argument that you can get by looking at that third column in the soup-based proofs. Okay? And if it turns out that the reasons you do things, partly like, for example, please shows, depend upon depend upon other certain things like that, okay? And they might depend upon things like some mumble is unknown, okay? Then you can often look at that part of the answer, which is the proof tree, and see what's missing. That doesn't answer your question completely, okay? But it gives you more evidence. In general, debugging is very hard, and we know that. And you know, this, I don't think this solves the problem of debugging, but it does have the property that many cases when something is broken, look, I got a box that's got something wrong with it. That means I stuff something, I put in information one end, the wrong thing comes out the other end, right? There's only two ways that can happen, right? Either one or more of the pieces inside that box is broken, or the way they're arranged is wrong, right? At one level, okay? So as an engineer, what I do is I get my volto milliammeter, my scope, okay? And I'm going to measure the input-output behavior of each of the sub-pieces, right? And if I find one of those is broken, then the problem is probably inside there, in which case I want to find the smallest box that completely contains my problem, right? And then that one will have the property that the pieces inside it are arranged wrong. That's a theorem that was incorrectly proven in my head, okay? And that's something I have to worry about. That's a different way of, that is the only way I know that really works for debugging. It's tracing by examining the pieces. Does that make sense?
It makes sense. The thing I'm worried about is that tracing what didn't, I mean, using what did happen to figure out why something didn't happen in the absence of more machinery would seem to be explosive.
Yes, it is, but I think that's true in any kind of programming. Okay. And I think what I'm suggesting is that since I have, in some sense, a mechanical model in my mind here, this is a wiring diagram. This is, in fact, to me, a program is a textual description of a potentially infinite wiring diagram where recursions and loops and things basically make more parts. Okay, but since it's a wiring diagram, then I do have the technique of putting in probes. Okay, and therefore seeing what inputs and outputs, how they relate.
Yeah, that was a good answer. So you expect A implies C, so you guess some intermediate B and you find out A implies B and B implies C.
Mm-hmm.
If one of those doesn't work.
Yeah. Yes.
You touched on this already, but do you have any favorite approaches for dealing with uncertainty other than probabilities?
No. I don't have any magic formula. I believe that probability is with high probability the best we can do. But I think the use of probability is very problematical. Okay, and that's the difficulty. I will. Yeah, go ahead.
Obviously, you showed 20 examples in the presentation. How big a real example have you generated in this field?
Oh, gee, we had that was nice. Well, By definition, but your definition of big, nothing. Okay, meaning what happens at Google. But there is an example which is way too big to put on slides, which is about a hypothetical insurance company called 8No. Okay? And this hypothetical insurance company is trying to decide whether or not people get insured based on their health habits. Okay? And so there are all sorts of things like, well, downhill skiing is dangerous, and skydiving is dangerous, and eating crappy food is dangerous. Like lots of hamburgers. And Danny Danny works at a hamburger joint, and and people who work at joints tend to eat the things that are in the joints, and so on. And so there's a fairly, maybe a couple hundred assertions associated with this. And the properties of 8No are that they're really very interested in having risk factors that can be accumulated. So and if your risk is greater than mumble, you don't get the insurance. If it's less than grumble, you do. And if it's somewhere in between, then it asks for more information. Okay, like it might. So it's not going to go looking up on Facebook whether they can find pictures of you that are eating a hamburger unless they don't have enough information about other things. Okay, so that kind of thing works beautifully. Okay, and it's about a few hundred assertions and a few and about 10 pages of code describing 8No and Danny and Hal and a whole bunch of other friends of mine. Okay, who all have bad habits. Okay.
Hand-coded, right? These assertions you had to come up
Yeah, they're all hand. I created this database by hand and created the rules, but it was sort of a demo for that I think is actually shows that because what I was really trying to show was how you can avoid doing work by knowing that you don't want to look at something that's unknown unless you have reasons to investigate it. That was the. So how do you work? How do you accumulate the reasons to investigate something?
Do you have something analogous to your hallucination example, where the people see the triangle? That's the white occluding triangle. Can we demonstrate a propagator hallucinating?
Well, I've been actually trying to get a graduate student to work on that.
Okay.
I haven't found one yet who's gutsy enough. But the idea, of course, is that you have some sort of quote retina, right? And what it has is that there are all over the place. There are little rules that are little propagators that connect neighboring regions, and the regions, of course, have multi-scale receptor fields, and what you want to do is have lined extensions and so on, things like that. And these guys talk to each other and jabber about it, and whether or not it'll work, who knows? But it's something like the waltz idea, but at the scale where you just fill your retina with the constraints. Okay. Mm-hmm. Yes.
Is there a rule that says if you assume A and then you get a contradiction, then we accept not A or reject A?
That's yes and no, because there might be many assumptions floating around. Mm-hmm. It's not just A. What if I assume A and B and C in various places?
Right.
Then I had better do some very clever choice of what to do, what things to retract to avoid the horrible exponential explosion that will occur. It'll still get an exponential, but I want it to be much smaller, right?
I think the question is whether you can write another network of stuff that will make the decisions about what to believe.
Oh, I think so. Yeah, sure. Yeah.
Parallel, you can't just use heuristic like the most reasonable stuff.
Oh, no, of course not. You don't have to do something like that. You can do much more complicated things. Yes, and that's easy, actually.
Right. If you accept B and C, then you have to reject A.
Yes, of course. But that's going to be, to a great extent, that's there anyway, because the way the causal learning works, which is the same thing as dependency directed backtracking, is you accumulate a set of no-good sets, they're called, which are the sets of assumptions that can't simultaneously be true, okay? Such that that if one set is smaller than another, then it subsumes the other, okay, getting rid of it so you don't have to look at it again, and that eliminates a very large number of possibilities for everything else. If these guys can't together be true, then it doesn't matter what anything else is. Like, Got it. Okay, so that clips off a whole piece of the tree of the search tree. Yes.
You mentioned that it's actually implicit outside of it. Have you actually evaluated it against state-of-the-art?
No, of course not. And this is not.
I mean, you cannot know machine against a single machine.
No, the reason, no, that's two parts to that. One is this: this implementation, like everything I get involved in, is very crude. Okay, I'm after ideas. I'm not going to sit here and tweak the code. Okay, so this is, it's not like I'm using the very best representations of sets. Okay, I'm using lists that are linear, perhaps. Okay, maybe not even sorted. In which case, intersections are square law, right? This is the demo. Okay, so it's because I'm trying to investigate the ideas. If I were going to do what you just said, oh yeah, but that's a year of work, and I wouldn't learn very much. Yeah, it might get somebody impressed, but I wouldn't learn very much. And I care about learning. Okay. I'm sure that there's no problem in making very high performance versions of something like this. Yeah.
So both of the examples you had with circuits and logic diagrams, work nicely because they can be decomposed into these clauses with two inputs.
With two inputs?
Right, it's like A or B, if A or B, then A, and A or B. In digital circuits, at least from my memory, you tend to often be able to decompose them into combinations of two inputs that.
Oh yeah, but the electrical, the analog models are not like that.
Right. So my question was going to be, does all this stuff still work if you have rules that are based on n inputs rather than two?
Oh sure, that's
okay.
Yeah, that's easy.
Okay.
No, it makes no difference. I have lots of stuff like that.
It just depends on the details of the formulae inside the cell.
Yeah, and they're easily arranged. Yeah. Mm-hmm.
Give it an arbitrary number of inputs and outputs and just write some code that connects them up.
Right.
So it's pretty arbitrary.
So you started by talking about psychology in your example of asking Arthur his name. And then we stayed in the logical domain and set aside probability. And the reason we set aside probability is doing any kind of sound probability is hard. But clearly the brain is what we're doing is we're taking in lots of noisy data, and in the noise there's contradiction.
Sure.
And we're doing some kind of unsound but fast probabilistic reasoning with throwing out outliers in the noise.
I would avoid the word probability. We're doing some fast mechanism.
Okay, we're doing some fast mechanism, but we're doing it over noisy data that contains contradictions.
Absolutely.
We're doing things like throwing out outliers.
Yes.
And forming pictures despite the fact that there were outliers we threw out. Why not just adopt some crude heuristics and just sort of admit some kind of very bad probability with crude heuristics so that the overall system can be more psychologically plausible in terms of the method.
That's sometimes the right thing. In fact, Jake Beal and I did something like that, and I can tell you about it. What we did, we had again, we're worried about how one might read text. I mean, of course, people make pretty good things for that, but how you would scan some text. So we had you looking at a sequence of letters or whatever. Okay, in straight text. So you're seeing not just the letters, but little chunks. And there are various patterns that we created propagators whose job it was to correlate. Okay, and if they would either sit on it or die. If they actually had the property that they made predictions, okay, that were acceptable, they would survive. Otherwise, they would die. And we made lots and lots of those. And we actually wrote a paper about this, and it got accepted in some conference which Jake gave a talk at, and it worked very well. Okay, but that kind of thing can easily be done. The question is whether or not it really has anything to do with psychology either. I don't know. One of the things, I'm very, very careful about this. I don't believe anything that's in that we call neurophysiology or psychology. That's because my friend Lettvin, who's now dead unfortunately, taught me that. And one of the most important things he taught me was this, that that's S equal 1/2 AT squared, right? That's how we describe it. It doesn't know that, right? We have to be careful to separate our description of what we see, how things work, from what the mechanism. I mean, the mechanism of this we really don't know, although Einstein came close to making it clear. But the behavior is easily described. Well, we observe smart people. Smart people seem to have some logic in them, and sometimes even they work probabilistically. Okay? So maybe we think that's our description of what they do. I don't know how it works. Okay, just think about how hard it is to imagine to understand how a brain works. Yeah, way back in the 60s, there was this PDP-6 at MIT that I used a lot. Okay, and we used to bring radios next to it and listen to the hiss. And every time the Lisp would garbage collect, it would go. That was the mark sweep. Okay, and things like that. Okay, but basically we had things like that, and there was the backplane full of soldered connections, hand soldered. I actually got some solder in my eye fixing one of them once. Okay, so there's a backplane. You can take your old oscilloscope. I suppose it was a Tektronix 547. Okay, with big thing with tubes in it, right? And I could put probes on these things and see spikes and so on. Okay, Now think about the following problem. Okay, suppose I have an infinite number of these. They're all slightly different. We have no diagrams. We have vaguely the big connection saying the big bus here goes to here. Okay, you can throw darts at it. You can cut a wire. You might blow it away with a gun. Okay, and of course the operating system fails in some interesting way. Okay, but you can't if you put a probe on it, you can't put it back in the same place. Okay. Are you going to tell me you understand how it works based on that kind of experiment? My feeling is that neurophysiology is going to give us some information in over about a few hundred years. The real value of it is medical. Okay, that they do a lot of study that we may learn how to fix people who are broken in interesting ways. Okay, but exactly how the machine works is just, I think, way beyond the technologies and mechanisms we have at this point. Even if you had the complete circuit diagram, it wouldn't help very much. Okay, look, we do have a creature for which we have the complete circuit diagram. What's this worm? C. elegans, right? Okay, they have exactly every cell, every worm of this kind is exactly like every other one. We have every synapse between all about 120 neurons, I think, in this thing. And no one can tell you, after studying for years, what that neuron does or how it creates the behavior that we see. Okay, so this is tough.
So just to be clear, I wasn't suggesting going through neurophysiology.
Right.
Keying off of the fact that
Yeah.
you started your talk off with what people do
Yes.
for a reason.
That's because it's inspiring. That's the reason. Okay, that we can see all sorts of things we don't know how to do that people can do. Okay, can we get insight into perhaps what kind of mechanism we as engineers can use? Okay, that might get us that kind of behavior. Whether or not that's how people do it is, I have no idea.
So if I follow things correctly, your propagator diagrams are basically a bunch of cells and a bunch of wires, wiring them together, and you're building the circuits this way.
Right, they're little boxes that are little functional devices.
Right.
Okay.
And you have a certain number of different kinds of wires.
Yes.
To describe what each relationship is.
Mm-hmm.
And then you can lay out the wires and you can say, okay, I've got values in these cells. Tell me what the values in these other cells are and how you got there. Right.
And you can dynamically build these things.
Right.
Right.
Have you looked at figuring out if you can do the system differently such that you have a bunch of values in these cells, a bunch of values in these cells? Tell me how things must be wired together and how these wires work.
No, I have no idea.
Okay.
That's cool. Of course, one thing you could try, but of course this is combinatorial disaster, is you have all possible connections. This is something like what of course Waltz did. You have all possible connections, and you modulate the assumption that this one is there, okay? And you do basically the SAT on that. But that maybe that sounds to me to be very unlikely to ever converge for any reasonable data set.
Right, somehow you have to figure out how you could actually infer things, right?
Mm-hmm. Yeah.
Right. It sounds like science, whereas what Jerry seems to be doing is more like engineering.
I think I'm doing is analysis. Analysis, actually. Right.
Right. I mean, you know, somewhere somebody figures out that, you know, the relationship between volts and amps and watts, and, you know, you could look at a bunch of data and say, okay, I know my voltage is this, I know my amperage is
There's this
this.
character at Cornell who seems to be doing that. Okay. By induction from numerical examples. I don't know how much credence to put in it, although it's been published. Okay. That is, I don't know how hard a problem can be solved. Remember, going back in history of AI, there was this guy, Psych. What's his? Doug Lenat, who had made a program called AM as a PhD thesis, and AM was supposed to induce mathematical truth from numerical examples, like, you know, there are prime numbers, and you give it, you know, it figures out the prime is an important idea, and that was a self-limiting process. It was sort of a wind-up toy, and I tried to tell him that at one point. It didn't matter. The thing is that it's easy to make those, and it's very, very hard to tell until you run them for a while how much of a wind-up toy you have. Yes?
Are there optimal paths that actually, if it probably works, that actually you can get to conclusion faster?
I'm not sure I know what. Say that question again.
I mean, these propagators to get information, they just do react and draw conclusions, right? Are there optimal paths that actually you can find that you can?
You mean through the propagator network?
Yeah.
Okay. Well, certainly it's the case that if these were all running really in parallel, which is what you'd hope in a really nice implementation, and then the ones that would get the answer to that place first would, you know, because there might be many paths, would do that. Of course, we have a lot of other things doing it too, and that's good. You have redundancy. Redundant ways of solving a problem are very important anyway. You know.
Yeah, I'm thinking about the first example about the triangle. If actually you follow a certain way, you get actually get the answer much faster than you just random bump.
I don't know if I don't see that. I don't know how that triangle thing works. The fact that, you see, because it's involving straight lines, and that's very weird because there aren't any straight lines in nature, really. So this is not something you would expect to be built in. Okay, so there's there is something about continuity there, and I don't quite know how this could possibly have been evolved. But people from places where there are no straight lines at all, living in the middle of jungles, also see kinesis triangle. So we know that this is not a cultural thing.
The horizon is a straight line. The horizon is a straight line.
It's the only one. If you see a horizon, if you live in the middle of the jungle, you're never going to see a horizon anyway. Okay.
Falling coconuts follow a straight line, not a static one over time.
They follow parabolas, but that's okay.
Very, very thin.
Yes, correct. That's correct. Right. If they have some horizontal velocity at all. Yeah. Yes, sir.
Just going to comment on the subject of sort of psychologically plausible results, that in some sense the correct answer is never very interesting because you can always get there by sort of convergent evolution. You don't know, you have no reason to believe you've gotten there by the same. And what's really interesting is to make a system that makes the same kind of mistakes we do.
Well, sure.
One
But
of my pet peeves is about CAPTCHAs, which I always have to go through 2 or 3 before I ever pass the stupid test. And what occurs to me is the mistakes I'm making are uniquely human, I'm sure. And so really I should have passed.
no, we can write programs that make mistakes too.
I'm sure that the form of my mistake would be different.
Remember, a computer is a mechanism by which a person can make 1 billion mistakes a second. Right? So no, I like to try to capture at least the way I like to think as programs. It sort of helps me to formalize it, and then I can try to debug myself and things like that. So I like to write programs whenever I see that I'm making mistakes. Yes. Look, I can run all night, so don't worry about it. Okay.
Are I assume you're probably aware of Carl Hewitt's predicate system logic and consistent logic work that he's been doing lately.
I haven't never understood Carl Hewitt, although I've tried. Okay, on the other hand, I've tried and learned a great deal from him because he's very, very smart. But I have no idea what he's doing right now.
Okay.
I haven't seen him in years. Okay.
It seemed to me that there was at least some amount of overlap between
There may very well be.
this and
Yeah, he's impressive.
Independently of AI or biological plausibility of how these things work, it's kind of an interesting computational model. And I find myself wondering whether it's a good way to organize large programs. So as a design philosophy, there might be a lot to recommend it.
Well, that's actually what as an engineer, that's what I'm worried about. What I'm mostly worried about, and I teach a class in this every spring term, is how does one engineer systems or write programs that have the property that they can be used in ways that are not anticipated by the designer? Okay, how do you actually build flexibility in? And I think that's very important. And I think it's if the pressure is on making correctness, then in fact flexibility suffers. Okay, you have to pay a certain amount of correctness for flexibility. And I could talk about that some other time.
Have you written anything up on that?
I've written flames. Okay? Large, complicated flames with many, many pages.
I'm curious what you teach in the class.
You come to,
Go look it up.
yes, it's called 6.945 and it will happen this spring. Okay, and I have no idea whether there's any old versions of it up.
Well, the old version that was taught here at Google in 2009, there's video for it.
But there's lots of it, but that's been major changes since then.
A lot of changes.
Yeah. Is there anybody else wants to give me a hard time?
You mentioned you had a whole lot of other stuff you could show.
Oh, well, I was good. Yeah, but that's always the way I am. I mean, look, the way I put this together is last night, basically spent till 3 in the morning pasting together this PDF. But indeed, I have other stuff. I was thinking about other ways. I'm not going to, I don't want to play you guys, but because I can, I know what I've talked. Here. I was thinking about here. Here's lots of this has to do with exactly. I can't use this damn thing. my screen is nice here. Come on, computer.
Just don't look at the big screen. Only look at the
It's going to China.
Yeah, what's going on here? Does anybody have a theory of this?
It's problem all over.
It's consistent.
It seems to me yours is worse than most.
It goes for data center.
Now, why is it not even running at all now?
Our infrastructure is bigger and is known to break all the time.
I see. Well, I think if you want to come look at my screen, I'll show you all of some nice things. Okay, I'm.
For the world at large, the infrastructure for a Googler often sucks.
Yeah, it seems that way. It looks like you guys have got a serious problem with keeping this machine working. Your screens. Oh well. I think the machine decided it's time to quit. Perhaps I burned out its bulbs. Okay.